All right, we're about to dive into a device that's so incredibly common, it's practically invisible. Yet, it's the hidden engine powering just about everything in our modern world. We are, of course, talking about the AC motor.
I mean, think about it for a second. What single piece of tech is the driving force behind the blades in your kitchen blender, the massive machines in a factory, and even the whisper-quiet acceleration of an electric car? They seem like they're from completely different planets, but they all share one powerful beating heart.
And that answer is the AC motor. It is the absolute unsung hero of our daily lives. So the real question is, how does this amazing piece of engineering actually work?
So let's start with the basics. What's its fundamental job? Well, at its core, an AC motor performs a kind of everyday magic. It turns electricity into actual physical motion.
Here's the core principle. An AC motor takes electrical energy from an alternating current, the stuff that comes out of your wall socket, and it uses the invisible force of magnetism to make things spin. It's really just a beautiful dance between electricity and magnetism.
Now, to really understand that dance, we need to meet the two main performers inside every single AC motor. So let's get introduced to the stator and the rotor.
Think of it like a theater performance. The stator, that's our stage. It's the stationary outer part, all wrapped in wire coils, and it sets everything up. And the rotor, that's our star performer. It's the part in the middle that actually spins, ready to take the spotlight. One creates the environment, the other puts on the show.
Okay, so we've got our stage and our star. How do we actually get the show started? Well, that spin is all thanks to a fascinating little three-step process rooted in physics.
Here's how it works. First, the alternating current energizes the stator's coils in a very specific order. This creates a magnetic field that doesn't just sit there, it actually rotates. Step 2, this rotating magnetic field sweeps across the rotor, and that induces a current inside of it, giving the rotor its very own magnetic field. And finally, step 3, these two magnetic fields interact. The rotor's field gets pulled along by the stator's rotating field, basically chasing it around in a circle. It's this constant magnetic game of tag that creates powerful, continuous rotation.
Now here's where it gets interesting. Not all AC motors are the same. Once you get that basic chasing principle, you come to a huge fork in the road. There are two major families of AC motors, and the difference between them is really, really important.
And the entire difference comes down to one simple little concept: slip. All it means is the tiny difference in speed between the stator's rotating magnetic field and how fast the rotor is actually spinning. Is the rotor keeping up perfectly, or is it falling just a little bit behind? That one question changes everything.
And this idea of slip leads us to our two big families. On one side, you have induction motors, also known as asynchronous motors. These are by far the most common type on the planet, and they actually need that little bit of slip to work. If there's no lag, no current gets induced in the rotor. Then, on the other side, you've got synchronous motors, and as the name implies, they have zero slip. The rotor spins in perfect locked-step sync with the magnetic field.
So this one difference, having slip or not having slip, creates two very different kinds of motors. You can really think of it as a showdown. The tough, reliable, everyday workhorse versus the high-tech, incredibly precise machine.
Let's look at speed stability for a second. An asynchronous motor's speed can actually dip a little bit if you put it under a heavy load. But a synchronous motor's speed, it's constant no matter what. So this makes the asynchronous motor simpler, more rugged, and cheaper. Perfect for a fan or a pump. The synchronous motor, though, is absolutely essential for things that need perfect timing and control, like industrial robotics or an electric car.
Yeah, a quote from our source material really sums it up perfectly. The asynchronous motor is the dependable workhorse whose speed can flex. Meanwhile, the synchronous motor is the precision machine that holds a perfect, constant speed. One is built for pure reliability, the other for absolute accuracy.
So, the next time you hear the hum of a fan, the whir of a blender, or see an EV glide silently by, you'll know the secret that's spinning inside. The real question is, now that you know the difference between the workhorse and the precision machine, which one are you going to start noticing all around you?